Okay. Do you see like 1/2 of a thing? Yes, like this thing?
Yeah.
Oh yeah, just half.
Okay. All right, let's start then. So when the system is at equilibrium, I mean, okay, some of these are like really easy, but I feel like a few of them are more difficult, so we can just go through all of them. Okay, so normally it's just me and MG, so I'm used to just like solving them. But do you guys want to take a crack at it? It's an easy one, so.
Okay. I like have no clue how to start this, so like we could just talk about it.
Okay, sure. So we just have to remember what equilibrium means here. And so equilibrium just means that the forward reaction and the reverse reaction are happening at the same rate. Okay, so it doesn't mean that either of them have stopped. They're just happening at the same rate so that it looks like they've stopped. So we can and it doesn't have anything to do with the actual value of the concentrations. Like there can be a ton of the products and very little of the reactants, and that can still be equilibrium. So we can eliminate A, and then like we said, it doesn't mean that either reaction has stopped, so we can eliminate B, C, and D. So this is a weird question. I wouldn't have chosen like this as the wording for the answer, but this is technically correct.
To find the concentrations, that's where the rice tables comes in, right?
Yeah.
Yeah.
Okay.
Wait, I have a question. So like for C, so it says both the forward and the reverse reactions have stopped. So like that wouldn't. Why wouldn't that be the answer? Like I know it's like wrong, but like how is it like different?
So at equilibrium, they haven't actually stopped. They're just happening at the same rate. So if they're happening at the same rate, it's like they're actively canceling each other out. So it looks like they've stopped, but they're both still happening. You just like can't really see it with your eyes.
I sent a graph in the chat. I would open that up. That visual really helped me when I was learning this, to see that the amounts don't change, but the reactions are still happening. They're just happening at the same rate. So you can look at that graph and see that.
Yes. Okay. So the next one, they're just asking for Casey.
Would it be B? Yeah.
Yes, indeed it would be. So you look at the coefficients, that's the important part here. So this has a coefficient of 2, and so does this one. So these two would be squared, and then it's products over reactants. And also make sure to remember to look at whether it's a gas, aqueous, liquid, solid. That's important because you don't include liquids or solids in the equilibrium constant expression. Okay. Okay, so this, you basically just find find KC and then plug in the numbers, and then that should work. So let's see.
You want me to annotate on there, or do you just
Yeah, sure.
Okay. Now, what happens if you plug that in? I'm not going to write down the amounts, but well, you have to. They give you moles, right? So you have to do moles divided by liter to find the concentration, I believe.
Yeah. Yeah, so it's 3 liters. So yeah.
So then you would plug in for NH3, would you plug in?
You would plug in.
Yeah, 0.0357.
Yeah, I think you plugged in the wrong one, MG.
Oh, what did I do? Oh, I plugged in N2. I'm sorry.
Yeah. So you do 0.0357 over 3, and then you square that. And then divide by...
I believe that's correct.
Yeah, okay. So what did you guys get as your answers?
I didn't plug it in.
I got. I like plugged in the wrong decimals, so let me just do it. Okay.
Wait, I got some really weird number.
I think you might have plugged it in wrong because I got the correct answer.
I got 24.4, which is not correct.
I got
Right,
198.78.
Wow, that's a lot.
Yeah.
Okay, actually, no, I think you're almost correct. It's 1.9878. So you're like I don't know why you got like.
Okay, I think I might have put the number in wrong, but.
Yeah, so just make sure.
I know what. Sorry. I know I plugged it in wrong. That should be a 0 here, not a 0.0357. Sorry about that.
Okay, yeah. So just make sure, like, I feel like like when you're actually plugging things in, it can get kind of difficult because there's many decimal places to look out for. But it's okay because multiple choice isn't really supposed to be calculator anyway on the AP Chem exam, so it won't be this complicated for multiple choice at least. But for FRQ, you should probably be careful about that. But yeah, if you just plug it in exactly as it's written here, you should be fine, I think. Like I got 1.99, so it would be B. Okay. So, okay, Shreya, what can you see about these two reactions?
They're kind of like the opposite. Like, I don't know how to say this, but it's like 5 and 2, and it's 5 over 2. So like, and there's 2 on one side, 2 on the other. The ratios are equal, I'm guessing. Something like that.
So it's like it's the reverse reaction and it's doubled on this one. So if this one is 4, so first when you're reversing, you do 1 over the forward. So it would be 1 over 4 just reversing. And then this is also wait, hold on, go back. Go back, sorry. Let me think because when you when it's since this is 2 times this one, it would be multiplied by 2. But I'm trying to think about whether it would be 1 over 8 or it would be, I think it would be, let me think.
Well, okay, so I would probably double it first.
Yeah, that's what I was thinking.
And then reverse.
That would give it 1 over 8 though, right?
That would be 0.125, which isn't an answer for
there. Okay, then.
Wouldn't you double it first? Because like you'd have to reverse the whole thing, or because you're not doubling everything. I don't know.
Wait, let me think. So the answer is B. So how did they get that? We can come back to this one. I'll just make a note. We'll come back to it. Number 4. Okay, all I know is that this is 1/16. So we have to think about how they would get 1/16. But yeah, we can come back to it. Okay, so Kc for this one is 0.02. Okay, these are the concentrations. So which is true about the system? Okay, so first we should probably see if it's at equilibrium. So just plug in the numbers. Okay, so I got 0.0125 for the constant. Did you guys get that too?
I got yeah, 0.0125.
Okay, so that is not equal to 0.020. It's slightly less than. So which is true? So as we said, yeah, it's less than Kc. So we can eliminate the other ones. And then if it's less than Kc, then to balance it out, we have to produce more products, right? So because we want
Chatelier's principle. You want to seek that
yeah,
equilibrium again.
Yeah, so because if we have a smaller QC than equilibrium, then we have to make it right.
Yeah, so a smaller QC means less products. So
Yeah.
if you want to get back, you need to push up the products and find that balance. So you want more products.
So it should be B, I think. Yeah, it's B. Okay.
Can we go back to the other one?
Sure.
So so right now the Kc for the initial one is D 5 over, I'm not drawing the brackets around, but
yeah,
D to the 5/2 C over
okay, I see now. Yeah,
B squared A, right? So now if we do Kc prime, that'll be we're taking this squared.
You're squaring everything basically,
right? Squaring everything, yes.
Yeah. Okay.
So I can say this is Kc is going to be or Kc prime is going to be Kc squared to the -1 and then I flip it. So it's 4 to the -2 power, and 4 to the -2 is 1/16. There you go. There's your explanation.
So yeah, that's what it was. So basically, since the coefficients turn into exponents, to multiply the exponents by 2, you have to square it. So we would square, you could do, and the order doesn't matter for this, I think. So you could square it and you get 16, and then you do 1/16 when you flip it. Or you could just do 1/4 and then square that and get 1/16 again. So that's why, yeah. So it would be B. Okay. Okay, we didn't quite learn dissociation, I think, like with percentages, but we can try it. Okay, yeah, we didn't learn this. Do you know how to do it?
Maybe, but I no, I don't know how to do this at this moment.
Okay, we can skip this one.
We could take it to Mr. Rogers tomorrow if we wanted to.
Okay, sure. But I also don't think it'll be on the test if we didn't learn it because we went by the AP curriculum.
Well,
Yeah.
first thing you can find the molarity of NOCl, and then if you find percent dissociation, that'll give you how much of that reactant turns into product.
Okay,
and then I guess
okay.
using that you can find the Kc. That would be my plan of attack. Now I'm not going to try and work this out right now just because I'm not confident in that. But if I didn't know
we can
anything
try
else,
it we can try it at the end if we
Sure.
finish early.
Sure.
Okay, so HI. Okay, so they gave us Kc, and they also gave us HI, the concentration of HI. So can you annotate like the formula?
Yes, I can.
Thank you for the reaction.
Okay. Kc is HI squared, concentration of HI squared over H2, oh my gosh, I2.
Okay, so we do 0.0706 squared divided by 54.6. Okay, let me do that actually.
We're isolating H2I2, right? Is that what we're doing? Okay.
So I got 9.13 times 10 to the negative fifth, and that is equal to the concentration of H2 and times the concentration of I2. And according to this problem, they have the same concentration. So we would, to find the concentration of one of them, we would just square root the value that we got in our calculator. So that should be, yeah, I think I got a
0.00955. Yeah.
Yes, it's A. Okay.
Sorry, give me a second. My mouse is acting up.
Yeah, sure. So we have, it's similar to the last one, we have initial concentrations of N2 and O2, and now they're asking for NO. So, yeah.
Write it out?
Yes, please.
Okay. It looks like it's practically the same thing, right?
Yeah, it is.
High and no.
Right, so 0.04 times 0.04, and then multiply that by Kc to isolate NO squared. So that should be 1.6 times 10 to the negative fourth. And then that's not our final answer because this is squared and we're just trying to find the concentration of NO. So again, you have to square root that. And then I got 0.0126, which is not here.
Wouldn't you have to use a Rice table for this? I don't know.
I don't think
this is initial concentration.
Yeah, it's initial concentration. You have to find the equilibrium concentration. So you probably have to use
Yeah,
Rice
okay.
table.
Okay, yeah, you probably do have to use a Rice table. My bad.
Okay.
So,
okay. Now I have forgotten how to do this, so you will have to walk through this step by step.
it's written like vertically.
Oh, yes. See that?
Yeah.
Clearly, I don't know what I'm doing.
Could you like explain how to do this? Because like I see Mr. Rogers do it, but it's really confusing.
Okay, so just write the reaction where it says R.
Do I need to put the coefficient down here, or do I just put, I know?
Just, I think you put the coefficient, right? You put the coefficient. I'm pretty sure you put the coefficient.
Yeah, you do.
Okay. And then so for initial, I'm assuming since they didn't tell us a value for an O, it's 0.
Probably 0, yeah.
Yeah. So then the change.
Oh, this is going to be, oh, I think I remember. This would be minus x.
Yeah, minus x plus 2x, right?
Yes.
Is it always that, like minus x plus x?
No, it's not always that. You have to look at the coefficients. So since like basically the mole ratio. So since it's 1, 1, and 2, like it's x and then 1 times x and then 2 times x. Like that's how you look at it.
Sometimes you'll have more products and reactants, in which case you'll do minus. Actually, you could even do it this way, and then you'll find x to be negative, and that'll indicate that it's going the other way.
Also, is this true? Like you always have to make sure that the left side matches the right side, like minus 2x and 2x, positive 2x, right?
No, not necessarily.
Okay, not true. Okay.
I wouldn't. I don't think so. Reason being, you might have a cubed up here, and depending on how the way it's balanced, I don't know. I wouldn't use that as a rule to check unless we've proven that, and I don't know that to be sure, because I can think of potentially you could have the coefficients not summing up to each other properly.
Okay.
For example, right here, 2SO, 1SO, that's 3SO, and you have 2 on the other side, so you're not going to have the same.
Okay, yeah. Yeah, so don't listen to me. Okay. So,
wait, I have a question about that.
Yeah.
So, I understand why, like, you have the XX and then 2x, but, like, could you explain, like, how, it's, like, negative again?
Oh, because, well, we have we have amounts of the reactants and we don't have any of the products, so it has to go to something. It has to, you need to create products. You can't just have 0 in the products. Like it can't be, you can't subtract from the products,
No, yeah, I know, but like, why is the x negative? Is what I'm asking. Like,
because you have to subtract from the reactants to
create
products.
Okay. I see what you mean. Okay.
That mass has to come from somewhere, right?
Yeah. Okay, that makes sense.
Yeah, basically you're turning reactants into products, so that's why it's negative. So then you have these concentrations at equilibrium, and then you can plug them in, right? Like 2x squared, and then, right?
I think so, yeah. You would do 2x squared over n2 0.04 minus x.
The whole square.
So what is this going to help you do? Oh, this helps you find, now you use this to find k.
Yeah.
Oh, okay.
Yeah, so you equate that to 0.1. So you have 4x squared. I guess you have to do algebra.
Yes, you have to do algebra. I think this is where you use that approximation thingy.
What's that?
There's certain instances where you have to, I don't know if this is the case where to do it, but you do a small change. I think it's called small change approximation. I would search it up, or something like that. And then because you assume that because the change is small, essentially this goes to 0, and now you don't have to do complicated algebra. I think.
That is what it was. It was in one of the AP daily videos. So
okay. Now you don't do that on the top one. You just do it when there's like minus or plus something, right? Otherwise, it would just be 0.
You assume that the change in x for this is so small that it's basically 0.04. Like even after removing, like just for the sake of calculating, you assume that it's so small that it won't really affect this. So you just use 0.04 for the bottom. So
okay, so let's say that goes to 0. So you'll have 4x squared over 0.04 squared, and that equals 0.1.
Yeah. So this concept is called small change approximation, if you want to study that.
0.1 times 0.04 squared is 0.00016. X, and now you using this, you can find X, right?
Mm-hmm.
X, I'll just write it off over here. X is approximately 0.0063. And because, as you can see here, we know it's a small change, like based on the calculation. But that's not what it's asking for. It's asking for the equilibrium concentration of NO, which is 2x, right? So we have to multiply that by 2.
Oh, okay. Okay.
I'm getting C. I don't know if that's what y'all are getting.
Yeah.
Okay,
Wait.
it's all coming back to me now. It's all coming back.
Right, so we found the value of X, and to find the concentration of NO, you have to multiply by 2 for the 2x, so it would be C.
Because it's 2x here, right?
Yeah, we just found the value.
Sorry, and the AP Chem test, we're allowed to use like our graphing calculators, right?
Yeah, I don't really think this would be a multiple choice question, honestly. This would be probably more of an FRQ, like if it had this much calculation.
I think he told us that in class. He was like, I would never make you guys do this, so probably.
Yeah. We can do one of the like more conceptual ones if you want, because this would be probably more likely to show up. Okay. So the forward reaction is endothermic. Okay. So which would decrease the equilibrium amount of H2O? So what would decrease the amount of H2O is if the reaction was pushed to the, if it was forced to be pushed to the right, if we added something to the reactants to like create too much like an excess of reactants, and we would have to push it to the right to get rid of it. So if we add not more oxygen, because that would be adding products and that would push it to the left. Adding a solid phase catalyst. I'm not sure what that means, so we're going to come back to that one. Decreasing the volume of the container, so the pressure increases. If the pressure increases, then what the reaction will want to do is decrease the amount of moles. So there's 2 moles on this side with the 2 H2O, and then there's 3 on this side with 2 H2 and 1 O2. So that's 3 moles on this side and 2 on this side. So this one would push it to H2O. So that's also not the correct answer.
So just to make sure I understood that right, if you decrease the volume, that's more pressure, and you want to get back to the initial pressure, so you were going to go to the side with less moles.
Yeah,
Okay.
It doesn't like that there's so much pressure. We're trying to decrease some of that pressure by going to the part with less moles. So this has nothing to do with anything. And increasing the temperature. Increasing the temperature. This is probably the correct one because it said endothermic in the question, but let's just think about it. So if we increase the temperature, then the endothermic reaction would be favorable because an endothermic reaction wants to take in heat. And
can I give you a trick?
Mm-hmm.
Whenever it says endothermic, I'll write down heat as a reactant on the left side, and then now you can see that. And if it's exothermic, I would write down plus heat on the right hand side, and then you can actually see that.
So if we're increasing the temperature, we're basically adding more reactant, and so that would, to counteract that, it would be pushed to the right to create more products. So that, like, it's Le Chatelier's principle, you know. So that would be D, I think. Let me check. Yes, it is D. So I still don't know what a solid phase catalyst is. I'm just guessing it's a fancy word for catalyst, I think.
It's a catalyst that's a solid.
Yeah. Okay. Yeah, again, this is probably pretty simple. It looks to me like it is. Do you want to give it a shot?
Is it? Oh, sorry. It's probably wrong, but is it A?
Okay, so it's the trick again. They tried to trick you and it worked on you. It's a solid here and it's a solid here. So yeah, so you have to pay attention to that. They're gonna try to trick you. So it would be C. Yeah.
Okay.
Very common. This is so common. I get these wrong all the time just because I go too fast.
Yeah, okay. So which of the following changes will increase the total amount of Cl2 that can be produced? So again, this is similar to the one we did 2 problems ago. So we want, if it's going to increase the products, that means something is added to the reactants that would push it to the products. So, or I guess removing, I'm not sure if that would do anything, but
yes,
so
it would.
adding,
adding something to one side is the same as taking something away from the other side.
Okay, so yeah, adding more ICL is here, so I think that should be correct, but I'm not, we can look at other ones. So removing the Cl2 as it is formed, that should also work. So now I'm kind of confused.
Look at answer choice E. Now you will be confused.
Oh. Oh, wait. Okay, would decreasing the volume work? Let me see. Decreasing the volume means that increasing pressure, and we want to go to the side with, but they both have 2 moles, so I don't think that would do anything.
Solid.
Oh, right.
Yeah, look at gas. Yeah.
Okay, so this has 1. This effectively has 0. So we want to go to this side. So that wouldn't work.
Yeah, because decreasing the volume will make the reaction shift to the left, right? Because once you've decreased the volume, you go towards more, you go towards the left. And
everything else seems like it would go to the right.
Yeah.
Right? The answer to this one is apparently it's C.
C?
But yeah, but I feel like A and B.
Maybe it's because A and B don't contribute to the equilibrium constant.
Oh yeah. Okay. It's because they're solids. We got tricked again. We got tricked again. Okay, yeah. So it's since they're solids, they don't contribute to the equilibrium constant. Yeah. Only Cl2 does. I can't believe they did it again. That's disappointing. Okay. Okay, these are all gases, so we're good with that. Since it's 1 liter, the molarity is the same numbers basically. A and B are added to this system, specifically this much. So
this has the scent of a rice problem, but I'm not sure.
Okay.
Does it seem like I don't know. Doesn't it seem like a rice problem?
I think so. Sorry, because you have to. It says increase the concentration. So
yeah, I think it is.
Yeah. Okay. They give us R, I, C, E. 0.2. So I'm not going to bother with sig figs right now because C is 0.4 and this is also 0.4. So now Shindana, I think and Neha, correct me if I'm wrong, but I think now this would be minus X, this would be minus X, this would be plus X, this would be plus X. The reason being you have more C and D than you have A and B, so you're going to shift to the, so now you have to.
Isn't the change just like this part?
Oh. Yes. Never mind. They tell you the change. So if the change here is 0.10 and this is also 0.10, then this has to be 0. minus 0.1, and this has to be minus 0.1, right?
But I don't think they're, I think it's just externally adding it in. Like, I don't think they're, do you know what I'm saying?
That's the point, right? If you externally add it in, the change in the other one has to be the same because of conservation of mass, right?
Okay.
That's why we were able to use a rice table, I think, because of that conservation. I don't know. This might be wrong. We'll see soon enough. Then this will be 0.3. This will be 0.3. This will be 0.3. This will be 0.3. So now you have 0.3 squared over 0.
Then what are we solving for?
The new equilibrium concentration of A. So wouldn't that just be 0.3 then?
That's not an answer.
It's not an answer choice, yeah. I don't know then. Oh, I'm sorry. Sorry, this is not even a rice problem. I don't know where that came from. You're adding this many. We have 0.10 moles. Wait, what?
I feel like this needs like the KC, right? For us to solve it. Oh no, wait, no, they give us KC, basically. But if we have all these values, that's basically KC. We have it then. Right? You just
but that's not the equilibrium constant. Oh, it is at equilibrium. I'm sorry, it is.
Yeah,
Okay.
So you do 0.4 times 0.4 over 0.2 times
0.4 squared over 0.2 squared, essentially.
Yeah, so that's 4. So the equilibrium constant is 4 for this one. And then, so if we add 0.1 and 0.1, we're trying to essentially keep the equilibrium constant the same. But the concentration of A, and I guess all the rest of them also have to be different. So
so are we saying 0.4 plus x squared over 0.2 minus x? I'm confused about what's happening here in the problem. I don't know how that connects to the math.
Okay, so we're adding 0.2 moles externally in there, right?
Yeah.
So, okay, so it has to be equal to 4. I can like tell what it's trying to do, but I'm not sure how to set up the equation.
Oh, okay. Let's see.
Thank you for the link.
I don't know if that's the correct one, but like.
What is the ideal gas law equation? Oh, in this case, it's K. Oh, we're finding KP, KC, same thing, whatever. Okay, so we found the KC. Now,
Did they get?
The values are different, I think. So are they? Yeah, they're different. So we can just look at like the method, not the values.
Mm-hmm.
All right, let me get rid of my working here.
Yeah, it's basically what we said then, right? Like plus x plus.
Yeah. Plus x minus x minus x.
Okay, it's kind of strange.
Maybe are they asking for a different? Is it a typo there? Because if they're saying that you start off with 0.2 molar A and you add 0.1 moles of A, then isn't the final just 0.3 moles of A?
No, because then it wouldn't be at equilibrium.
Oh, okay. So that means we're, okay, so then maybe the initial value is 0.3, 0.3, and this is still 0.4, this is still 0.4, right?
Yeah.
That's initial. Now change is going to be plus x, minus x, minus x, right? Because there's more
No,
of
well,
this.
it's the other way, isn't it? We added, like, do you get what I'm saying? Because we added to A and B.
Yeah. Yes, sorry. Actually, honestly, it doesn't matter. Because at the end of the day,
I guess it
you're
doesn't
gonna get a
matter, but-
negative x. But yes, conceptually, you're right. We should do it. I think it makes more sense to do it this way. But just don't freak out is what I'm trying to say. If that happens where you mess up and then you'll just get a negative x. Same idea. So now you'll have your equilibrium. You add these together. For the sake of space, I'm not going to write it out. Then you'll have 0.4 plus x squared over 0.3 minus x.
So it was rice table after all.
Yeah, it was a rice table, and using the initial condition, and we found that Kc was 4, right?
Yeah.
So now we can take the square root to get rid of these squares, and you'll get 2. You have 0.4 plus x over 0.3 minus x equals 2. Now it's a matter of algebra. 0.4 plus x equals 0.3x. No, sorry, 0.6 minus
3x equals 0.2.
That means 3x equals 0.2.
Mhm.
Is that right?
Yeah.
Okay.
I think so.
And then x equals 0.0667. Is that what it is?
That's not the correct answer.
But that's x, right?
Yeah.
0.0667.
So that's the change. And then so if we're trying to find the actual concentration of A, you do 0.3 minus 0.0667.
Yes. And which would be the 0.23, I believe.
Yeah. Okay,
Why
that was a
did you
lot.
set it equal to 4?
We found it earlier. Remember, we just did like 0.4 times 0.4 over 0.2.
Okay.
They tell you that that's at equilibrium, so you can use that.
Oh, okay, right.
Yeah. So we just found the constant here. Okay, I'm tired of the number ones. I just prefer these. All the answers right there. Okay. Which of the following statements can be made about K, the equilibrium constant? Okay, you can just read it and tell me. You guys can tell me if you have an answer.
We're doing 17? Sorry.
No, 20. I just didn't scroll down because the answers are right below.
Okay.
Would it be C? I think he told us one class that the only thing that affects the constant is temperature.
Yes, it is C because of the reason you just said. I know he actually told us the like reasoning behind it. I don't remember it right now, but
temperature increase. For why it increases the K.
No, that why it's the only thing that affects the equilibrium constant. Temperature. There's some reasoning, I don't know, but just remember that
well, we know we can rule out B and D for sure, right? Because that doesn't change the constant, it just changes the concentrations themselves.
Yeah.
E, I don't know, but let's see. Temperature will affect.
No, it doesn't change anything. He said that too.
Yeah. Oh, it's a matter of Le Chatelier's principle with K as well. But let's say Adding heat will shift the equilibrium to the left. This is an what is this, endothermic? Okay. Anyways, adding heat will shift the equilibrium and will result in a larger denominator, and hence the value of K will become. Okay, essentially, you can work it out with Le Chatelier. It changes the concentrations on both sides.
Okay.
Okay, the one way to, I would think of it with that idea of like, kind of like heat, like as a reactant. Wait, why can't I annotate? Where's the?
Oh, sorry, I paused it. 1 second.
Oh.
Okay.
Okay. So let's say you have A plus B goes to is in a reaction with C and D. Okay. Now, if it's endothermic, you have heat as in, like, I'll put it in parentheses. It's not really a reactant, but you can think of it as one. Now, when Le Chatelier, if say you add heat, so initially your K is CD over AB, right? Now, whenever you add heat, you're shifting the equilibrium to the right. So whenever you've added heat, the equilibrium constant is now it's some new C, some new D over some new A, some new B. This you can't do a rice table with, because when we do rice tables, we make the assumption that K is the same.
Yeah.
And when we make that, that's what allows us to find that change in X. But whenever this happens, the equilibrium itself shifts because you've added in more heat.
Okay.
That's
so
how I think of it.
I have a few more questions that I have a few more questions. 1 minute. Let me just figure out how
I
to do
have to
this.
leave. Thank you so much.
Okay, yeah, no problem. Bye.
Bye.
Can you duplicate Word docs?
Yeah. I would probably just copy and paste it.
Oh, that's
Copy
hard.
the file and then paste it. I'm sure maybe there's an easier way. Or do you want to like duplicate the window?
Yeah.
Oh, go to the view pane, I think. Or it might be in review. Let me open it up myself and see. It's in view or review, and then there's like multiple windows, I think is an option. You see that or no?
Multiple.
Here. Okay, I opened up.
New window? Is it new window?
I think so.
Okay, yeah, I got
Did
it.
it do it?
Mm-hmm.
Okay. Yeah.
Okay, let me just go back to the place where it was. Okay. All right. So this is KP. Fun. Change. Okay.
All right. See you, Shindona.
Bye.
Thank you for the reaction.
Okay.
Okay. We're doing 31?
Mm-hmm. Okay, so you just do 2 squared, which is 4 over 1, which is 4. So that's less than Kp. So at equilibrium, the partial pressure of BRCl will be greater, right?
I believe so. Think so, because you're going to shift to the right? Because
because
Q is less.
Because Q is less than K, we need to make it bigger by increasing products. So it should be D. Let me see. Yep, it's D. Okay.
Real quick, how do you tell when the total pressure increases? That's something I always got confused by.
Mm,
Do you just have to do a rice table for that, or like because I don't know how else. Can you just
I'm kind of
conceptually know that?
confused on what you mean.
So do you see how there's an answer choice C? It says the total pressure will be less than the initial total pressure. How do you determine when the total pressure is greater than or less than when there's a certain shift in equilibrium? That's okay. We can come back to that.
I
That's
don't
just
know.
a
I
question.
have no idea actually. So yeah, I don't know. Okay, sorry.
It's okay.
Kc has a value of 4.62. These are the initial concentrations. Okay, yeah. Again, you just figure out which direction it would go in. Okay, what did you get for the Q value?
Sorry, I've just been sitting here and staring.
Oh, okay, that's fine. Yeah, I got 30. I got 30, which is obviously much bigger than 4.6. So I think it should go to the left. B. Yes, B. Okay. Which is true.
B is obviously wrong. We've discussed why.
Yeah.
Here, let me. Okay. K does not depend on the concentrations or partial pressures of reaction components. I think that's true. Wait, what does it mean by depend? See, that word depend always messes me up in physics too. Like, does that mean like dependency as in like just a mathematical dependency or like a...
I think that's what it means. So that's
Then that would be false then.
Yeah.
Yeah.
Okay, yeah, wait, no, I didn't even see E. Yeah, that's obviously true then.
Oh, yeah. Yeah, that's, yeah, by definition.
Yeah. Okay. How is the reaction quotient used to determine whether a system is at equilibrium? Like it's the same thing, basically.
Yeah.
I think it's E. Yeah. Okay. Adding N2 at equilibrium will result in... Okay, it should go that way. It doesn't affect equilibrium constant, as we said.
Shouldn't, yeah.
It should result in a decrease in H2, which is
I would think so.
Yeah. So guess because if everything shifts to the left, then H2 will also decrease. So
And E is way too extreme, like removal of all of that.
yeah.
We don't know that.
Yeah, it's not gonna say all. It might say like virtually all in like some cases, but it definitely won't say all. Okay. So I think it is B, yeah. Adding O2. It doesn't affect equilibrium constant, so we can rule out C and E. Partial pressure.
Well, it's going to shift to the left now, right? Because we've added stuff to the right.
Okay. Yeah, so it should increase the partial pressure of
carbon monoxide. Oh, sorry, carbon dioxide, yeah.
Yeah.
Increase.
So D?
Yeah, D.
Yeah, it's D.
Okay.
An increase in temperature. So this is an exothermic reaction. So temperature in this would be a product. So by increasing temperature here.
Oh, we're increasing temperature here, right? Exothermic, so heat is a product. So if we increase temperature, we're adding heat.
Okay, yeah. So it would go to the left.
Yes.
So it would probably be A.
Oh, sorry, not B. Let's increase the partial. No,
Wait, no,
not A.
my bad.
No, it's okay. I read it wrong too. A's wrong. B's wrong.
Wait, how can they all be wrong? This is weird.
Decrease the value of the equilibrium. I think it's either C or D. Increase the partial pressure of CO.
So if it goes to the left, then that would decrease the value, right?
Yeah, I would think C. Yeah.
Because we have more reactants, so C is correct.
Good.
Okay. Again, an increase in temperature, and again, it's exothermic. So it would push it to the left again.
We just saw that it can't be an increase because we just saw that in an exothermic, if you increase the temperature, then it's going to be a decrease in K, right?
Yeah.
It can't be C.
I can't. Okay.
Shifting to the left.
So SO3 would decrease, right?
Yes.
A? Okay, yeah, it's A.
Yeah.
Okay, only.
I feel like this is more like what you're likely to see.
Yeah, I hope it's better. It requires more like thinking than plugging in the numbers.
Yep.
Okay. Which will shift to the left in response to a decrease in volume?
Less volume, more pressure.
Yeah, less volume, more pressure. So we're trying to see which one will shift to the left. So the left has to have less moles.
Yes, because less pressure, more pressure means we want to go to less moles. Yeah.
Yeah, okay. So here there's 2 on the left, 2 on the right, so that's equal.
Yeah.
Here there's 4 on the left. Wait, this is just okay. Okay. This has 4 on the left, 2 on the right, so that's wrong because we want less on the left.
Yep.
This one has 3 on the left, 0 on the right. I wasn't tricked this time.
Yeah, I wasn't tricked this time either.
Wait, this one is 2 on the left, 2 on the right. Okay, well, we just eliminated all of them, so.
Well, maybe I think B might have been a typo.
Oh, really? Okay.
If that was like that, yeah, that would make sense. Okay. I think the equilibrium, yeah, it would have been B then.
Okay, yeah. 39, yeah, B. I was so confused.
Yeah, they're not gonna do that on the AP exam. They're not gonna trick you and put like a random.
Okay. Increasing pressure, not change. Okay, so this one, it would be equal amount of moles on the left and the right. So this has 4 on the left, 2 on the right, 1 on the left, 2 on the right, 3 on the left, 2 on the right, 3 on the left, 2 on the right. Okay, yeah, so it's E. Yeah.
I don't know why, but I get scared when I go through A, B, C, D, and none of them.
Yeah, me too. Sometimes I do, like, I go in between, like I go from A to E. To
yeah.
I don't know why I do that.
Yeah, just to change it up.
Okay, this is exothermic, so it predicts that
heat on the right side.
Okay, so it'll have to do with temperature probably. Increasing temperature will push it to the left. So I don't think that this is true actually, right?
We want to increase the number of moles. If we increase the number of moles, we want to go to the left. So we want something that will push it to the left. Increasing the temperature will push it to the left.
No, it's SO3.
Huh?
SO3.
Increase the number of, oh, I'm sorry. Yeah. Okay. Then E is,
so I think it would be E. Right. I think it'd be E, just looking at it, because
you increase volume, you're decreasing pressure.
Oh wait, no. I thought it was, okay, never mind. I thought it was decreasing volume. I read it wrong. Because I feel like if you decrease the volume and increase the pressure, you would want to go to the right because there's 3 moles on this side and 2 on this side, right?
Yeah, so E would be wrong then, right? Because
oh yeah, it's essentially, this is the same thing as B. Oh my god, okay. But
I hit Control Z on my
Okay, yeah.
Oh my, okay. It
So
can't be
E is essentially the same thing as B. So we can eliminate B as well. So
Yes,
it's gonna
and
be A,
E's
actually.
wrong. It's going to be A. Yeah, E. Yeah,
Yeah.
obviously you can't decrease and increase the pressure. So if it's it would be A.
Yeah.
Then.
Wait, yeah, actually I didn't think of that. Okay, yeah. Endothermic. So what will
E1.
result in it's probably gonna be one of the temperature ones then.
Yeah. More CO2 means to the right.
More
Oh wait, but look
yeah.
at this. It's solid. We don't want to be fooled by them again.
Right. I don't think that matters.
Yeah, but in this case, it doesn't matter.
Yeah, okay. So it would be A, I think.
Yes, increasing temperature.
Would push it to the right. Okay.
Yep.
Catalyst. Catalyst? I thought we said it doesn't do anything.
Catalyst increases the rate of reaction.
Right. Without changing the composite. Okay, I think it's D.
The rate at which equilibrium is achieved without changing the composite. I think D. Yeah.
Yes, it's D. I don't
Is
think
D?
it has
Yeah.
any. I don't think it has any effect on the equilibrium constant.
Yeah, I don't think. Yeah, catalyst. Let me just. Yeah, temperature is the only thing that affects the equilibrium constant. So yeah, catalyst.
And I don't think you can increase the rate of forward reaction without also doing reverse reaction, right?
Yeah, that doesn't. Yeah, that doesn't make sense.
Okay. Removal of some C. Okay, so that should push it to the left.
Yeah, Casey's not going to change. Oh wait, remember it's a solid.
Okay, never mind then.
So would it be?
So no further change?
No further change, I believe.
Okay, yeah.
Because everything else is a gas.
Yeah, that's correct. Okay. That's gonna trick me at some point.
Yeah, it always, yeah.
Okay.
Okay. I don't like these questions where they give you the same graphic and you have to like do multiple questions.
I don't like them either. Adding I2 would push it to the right. So I think it's this one. This looks like an addition.
What is on the y-axis? Oh, it's concentration, right? Yeah. If you're adding I2, obviously that's increasing. So A.
Yeah, A. And then removing Cl2. So that's probably this one.
So we have to look here. If you remove CO2,
it's probably this one, right? D.
You're gonna get an increase in ICL.
It doesn't even show ICL here.
Oh. But this is decreasing. Oh, is it just talking about like this is where you decrease the CO or remove the CO2?
Yeah.
Okay. Yeah. D.
Okay. Increasing temperature would push it to the left.
More I2, more CO. More I2, less ICL.
Yeah, so it's B probably.
B. Yes.
And then increasing volume.
Increasing volume means less pressure. Less pressure means we want to go to more moles. There's more moles on the right. Or there's the same. It's the same.
It's the same.
Yeah.
I don't really know what this is. Okay, let me check the answers. So A is correct for this one. D is correct for this one. B, this is supposed to be C. So I'm not
48
sure.
is supposed to be C?
Yeah.
I see. I guess that makes sense because the concentration is the same at the end. Or it's unchanging at the end.
Oh, okay.
Wait, but that doesn't make sense because everywhere else it's also unchanging at the end. Hold on.
But also, shouldn't this drop be like larger? Or it shouldn't be the same, right? Because this is 2
I would think so. Yeah, I would think it would have to be double.
Okay, that's interesting. We might do a couple more and then let's end at 7:15.
Sure.
Okay. Heat is applied to the system. Okay, here is when heat is applied. So when heat is applied and the reactant drops and product increases. So it's It's
Heat
it's
is added, so heat would have to be on this side. So if heat is
yeah,
added.
endothermic and KEQ should increase because it'll create more products.
More product, yeah.
So
C.
yes, it is C.
Okay.
A stress was applied. What is the stress? Oh, that's the question.
So H plus.
Someone drew this.
Yeah, someone. This is decreasing, right? So if this is decreasing, so this is the change. Oh my gosh, the change is happening this way.
Yeah. Okay, I think it might be C.
You add the base. What is that? Oh my god, what is that? Is that acetate? No. What is CH3COO minus?
Isn't it sodium acetate?
No, yeah, I know it's sodium. Okay, I just wanted to. I forgot the name of the polyatomic ion. It's acetate, right? CH3COO minus.
I think so.
Okay, so then yeah, sodium acetate. But really, effectively, what we're doing is we're adding acetate because this is an acid-base reaction, I believe. Yeah, it's an acid-base reaction. So we're more concerned about the acetate itself. So yes, if we do add acetate, then we're going to shift to towards the left. C, I think. Is the right answer.
Yeah, it is C. Okay. So the value of KEQ. Okay, this is just the same
flipped?
thing reversed. Yeah, so 1 over 1.135. 7. So I got D. Yeah, it's D.
Okay. Oh wait, hold on. 1 over 0. Oh, sorry. I got 0 and I realized I put 0 in the calculator. Of course, 7.4, right? Yeah.
Yeah. Okay, it's 890. Okay,
we're just halving everything, right?
Yeah, it's
that means we're raising everything to the half power.
To the power of a half, yeah. So 890 square root. Nope. And then 1 over that.
Wait, why are we doing 1 over? Did it flip?
Oh wait, my bad. Yeah, flip, not 1 over. Not 1 over. It didn't flip this time. Okay. So it should just be C, I think. Yes, C.
Yep.
Okay, the value of KEQ is 0.2.
Doubled everything.
Doubled? Okay, so square it. Okay, so my mind. Okay, it's fine.
You know, the more I do these problems, the more I realize chemistry really is just a math class.
It's nice. I like it.
It is nice. I think it definitely sharpens your math skills, but I think that's kind of why I think physics I find more interesting.
I like both.
No, they're both nice. Yes, I agree.
I keep doing that. Okay.
I was about to hit Control Z again.
Yeah, so it should be B, I think.
Yeah,
it's B. Okay. Let's do these last 2 questions and then end it. Yeah, so this is half and it's flipped. So
half and flipped. So raised to the half power. 54 to the, or I just like to do it all at once. 54 to the negative half power.
Oh yeah, that works too.
0.136.
I got C as well. Okay. 6.5 times 10 to the negative second. Yeah, so this is flipped and to the power of a half again.
Negative half power. Okay. 2.92.
I got 3. Oh, you said 3.9?
Yeah, 3.92.
Okay, yeah, I got that as well. So.
Also, if you see a negative K, you should immediately rule that out just because K can't be negative to my knowledge. Yeah, okay.
Okay, that was a good session.
All right, yes,